Good morning, everyone. We'll be starting class in 1 minute's time. Good morning, everyone. And today's lecture is basically going to be a recap of what we refer to as the Continuous Time Fourier Transform, or in its acronym term, the CTFT. So this is basically just a recap as to how we use the Continuous Time Fourier Transform in particular, and how we do plan to use it going forward to formulate what we refer to as the Discrete Time Fourier Transform, which forms the basis of the frequency analysis transform that we use throughout the entire course. Follow along with that, eventually you'll see how the Discrete Time Fourier Transform, also referred to as the DTFT, approximates towards the Discrete Fourier Transform, which is referred to as the DFT, and then how do we move towards a more popular version of the transform known as the Fast Fourier Transform, which is also referred to as the FFT. But that's along the course lectures over the next 2 weeks, and when we actually hit the FFT lectures, we'll actually start applying the FFT towards numerical sequences and as to how we can actually perform the frequency analysis on those numerical sequences in a discrete time fashion. Alright, so let's start with today's lecture. So typically, any audio signal that we try to send through some sort of channel, and in this particular example, a telecommunication channel, can be decomposed from the time domain into its frequency domain representation, and this frequency domain representation can be used such that we can do frequency domain analysis to extract characteristics of the signal a lot easier. Typically, when we do this, we also refer to this as obtaining the frequency response of the signal. And the frequency response of the signal will always have some sort of ST referred to as the centralized frequency. And then there will be the individual sidebands, which we refer to as F LSB and F USB, which refers to the lower sideband and the upper sideband accordingly. But for our case and argument for now, we'll just be focusing on the centralized frequency for any sort of sinusoid or a periodic waveform that we'll be dealing with. So let's say in the instance, if two people were speaking throughout this telecommunication channel, when you watch this in the time domain, it's not easy to realize the differences. But you might see some amplitude differences, yes, but you're unable to see any sort of time difference whatsoever. However, when you move it to the frequency domain, you actually see that for this solid waveform here that we observe, there's going to be a unique centralized frequency compared to this dotted waveform, which will have also its own unique centralized frequency. So, like I said, the purpose of doing the frequency response analysis of the time domain signals was such that we could extract out characteristics of the waveform a lot easier. And it's a lot easier as well to do any sort of signal processing because of the frequency domain characteristics of these signals. In particular, One field of study that uses this heavily is what we refer to as speech analysis, where we can do speech recognition and speech identification. Frequency domain analysis is also used in different fields of application. So as of such, like if you have an equalizer on your stereo, you can always adjust the bass and treble and voice. Bass tends to be low frequency components, the voice tends to be the middle frequency components, and the treble tends to be the high frequency components. So the higher you slide up those equalizers, you increase the gain, so you get better bass or better treble and so forth. The lower you slide it down, you reduce the gain, so that way you mitigate it and so forth. In power systems, frequency domain analysis is used heavily in what we refer to as harmonic analysis, where in power domains, harmonics can be very detrimental towards your systems, such that they can actually destroy them. So they do harmonic analysis in order to figure out, okay, how do we filter and mitigate these harmonics from destroying our systems accordingly. In the stock market fluctuation analysis, frequency domain analysis is actually used to predict when the stock is going to rise or fall based on the past values, as well as in some cases, because of advances in machine learning, it also predicts using certain news articles as well. They say, okay, is this a good indicator that the stock is going to rise, or if this is going to be a bad indicator that the stock is going to fall, and so forth, to make these predictions as well. And the frequency of these news articles also indicate, okay, maybe this is something that's really good, or this is something that's really bad, and so forth. Frequency domain analysis is also used in like in audiology and image processing and so forth. And it's basically used anywhere where you do encounter some sort of signal that has multiple frequency characteristics. So the frequency content of any signal is what we refer to as its spectrum. And the information about the frequency content is what we refer to as spectrum analysis. For continuous time signals, you need to get a piece of expensive machinery here, as outlined by this image, which we refer to as a spectrum analyzer. And this machinery itself costs like a good bit of money, somewhere in the tens of thousands of US. So doing any sort of continuous time spectrum analysis always tends to be pretty costly in some form or fashion. But if you're doing discrete time frequency analysis, it's a lot easier, because now you have just to get a computer to actually do this analysis for you. So typically, when we are introduced to the Continuous Time Fourier Series, the analysis of doing this for any sort of periodic signal is that we can express this in an infinite sum of orthogonal functions, meaning that it will be an infinite sum of cosine waves and sine waves, which formulated a Fourier series. And each one of the frequency multiples of this Fourier series was basically an integer multiple of the fundamental frequency, which we also refer to as our upper sidebands and our lower sidebands of the sinusoid wave itself. The guy who invented this was Jean-Baptiste Joseph Fourier, and basically he was credited with the invention of the Fourier series and the Fourier Transform by extension somewhere in the late 17th or 18th century, if I remember correctly. But we still use his mathematical invention today for our frequency domain analysis. So typically, let's say if we had some square wave here, it's possible to actually apply the Fourier series to obtain its representation of cosine waves and sine waves as such. So the first four terms of the Fourier series, you may actually see this when we start doing this, but when we add the four terms itself, you see that it starts to approximate closely to what the original signal is as of such. And if we increase the number of terms, we'll get even more and more close to what the actual signal is, but we start adding those terms together in the Fourier series. So any periodic signal can be expressed as an infinite sum of sinusoids using the Fourier series, where the sinusoids will be cosine and sine in nature. From this point forward, the form of the Fourier series that we're going to be doing for our analysis will be the complex exponential form, which is basically the summation notation with the CK component and the exponent Euler component here, where the CK component is equal to this fancy integral of the original continuous time x of t signal using the Euler expansion component here as well. Remember, this Euler expansion component is basically sine and cosine just added together accordingly as is. So I believe in this case, because it's e to the minus jk omega naught t, that Euler component here extracts out such that it's going to be cosine of theta minus j sine of theta, where this theta here will be equal to, if I am saying this correctly, k omega naught t. I'll double check this just to make sure that I wrote the right thing. If I did not, I'll correct it on the slide accordingly as of such. So in using the complex exponential form here, we have the CK component, which basically gives us our full magnitude and phase of our complex Fourier coefficients. The CK component here is also equal to that fancy integral that we just saw. But we had this K component here representing where we will be analyzing the frequency component as such. So when k equals to 0 here, we'll be at the central frequency, but then when we go to the 1 and 2 here, this will be what we refer to as the first harmonic and the second harmonic accordingly. And we'll basically obtaining the magnitude of these harmonics. And you can do a little bit of further analysis as well to obtain the phase of these harmonics as of such. So this CK component here, because it's a complex exponential form, it's possible to get the magnitude of CK, which is given by the modulus of CK here. And this plot of the modulus of CK versus angular frequency is what we refer to as the amplitude spectrum of the x of t signal here. And because we have the exponent component, we can shortcut this into e to j phi of k. The plot of phi of k here versus angular frequency is what we refer to as the phase spectrum of x of t. K here is always going to assume integer values. So all the amplitudes and phase spectra basically appear at what we refer to as discretized frequencies, which is going to be multiples of omega naught here. So it's going to be k omega naught. So like I said before, when k is 0, we'll be at the central frequency. But when k is 1 and k is equal to 2 and 3 and so forth, you'll be at the first harmonic, which will be omega naught. Then the second harmonic, which will be 2 omega naught. And the third harmonic, which is referred to as 3 omega naught, and so forth. So let's recall the example, which is a very common case where we have our nice square wave here. If you actually perform the CK analysis of this being the Fourier series coefficient, we'll get this sine formulation here, or the sine equation here, sorry, which is going to be sine k pi a on t divided by k pi a on t, which is basically what we see here in the brackets. And a shorter way to write this is, once you have sine of x here divided by x, this is what we refer to as sinc of x. So that's a shorter way to write this equation here in particular. This equation is what we refer to as sinc of x, where x is the component in the brackets here. If we plot this accordingly with respect to t and magnitude, we basically see here that it gives us our nice sinc wave as of such. Now, one thing to note here is that as t increases, the lines here will get closer together. So conversely, as a decreases, because a is on the numerator here, this k pi a on t here, which we're going to be referring to as mt on a, will increase accordingly. So that means that the zero crossings here, where we have these zeros here on the x-axis, they'll move apart and the curve itself flattens. So remember, k here is equal to mt on a. So k here is equal to mt on a, where m goes from negative infinity to positive infinity, which can be integer values. And as a decreases here, mt on a here being equal to k will increase. And as that increases, this curve itself flattens and the zero crossings move apart. So if t increases here as well, and these zero crossings move apart and the curve flattens, that means the pulse train spacing here increases. So the spacing between pulses here increase as well. And in doing this limit evaluation, we'll end up with what we refer to as a single pulse. And the spectrum of a single pulse is what we refer to as a continuous sinc function. Conversely, if A here increases, this zero crossings here decrease. So the curve itself compresses together instead. And the single pulse that we had initially, which was this flat line, will now move towards compression, giving us such that the single pulse will approach an impulse. So the spectrum of an impulse here is what we refer to as an infinitely wide sinc, which is also referred to as a flat spectrum. So repeating this again just to explain what happens. So when A itself decreases, this zero crossings here, they go apart. So they move apart. So basically the entire curve flattens. So the curve here, if we decide to plot it, will just end up being the straight line here, because how it flattens entirely. And that's because the zero crossings move apart as A decreases. Conversely, that also means as t increases, we also get that same effect, because t here is on the denominator as of such. Once we get this flat line here, this is what we refer to as a single pulse. And if we take the spectrum of the single pulse, we'll get a continuous sinc function altogether. As A increases, the zero crossings, they get closer and closer together, so the curve itself compresses. If I raise this part here on top, because the curve compresses, that means that we approach an impulse instead. If we take the spectrum of the impulse, we get an infinitely wide sinc, which is basically going to be a flat spectrum. And that gives us the point where if you take the frequency response of an impulse contains all frequencies. So are there any particular questions regarding the explanation of this slide at this point in time? Alright, it doesn't seem like we have any questions, so let's move along. So in observing this, is that a periodic signal itself has what we refer to as a discrete spectrum, because we can see here basically gives us our stem plots accordingly for each instance of k that we may observe. Just ignore the x-axis for now. I know it says 1, 2, and 3 and so forth, but this basically, for any instance of omega naught that we can think about, we will get a discretized spectrum point as its edge. So as the period increases, like I said before, that's the same thing when we observed our effect when A increases and decreases. So we obtain the same effect that we just observed on the previous slide. So because of that line space in here being pi a on t and k is equal to mt on a as of such and so forth, as t increases, those line spaces themselves decrease, so the spectral lines get closer together. And the zero crossings move further apart, so that is such that the spectrum itself flattens. The Fourier series itself applies towards periodic signals, but the Fourier series itself can be applied to non-periodic signals, such as speech. So before we actually move towards formulating how the Fourier series is used for non-periodic waveforms, we need to answer the question here is what's going to be the period of a non-periodic waveform in particular. And in treating with this, for any non-periodic signal, so we need to re-observe the effect that we just now observed when t increases here as of such. So the period of a non-periodic signal or aperiodic signal, what we also refer to it as, is that we treat this periodic waveform with an infinite period. No, sorry, I said that wrong. We treat the aperiodic waveform such that it is a periodic waveform with an infinite period. And as of such, we assume here that t itself, being the period of that aperiodic waveform, tends towards infinity. In doing this, that means now we have to do a limit evaluation on the Fourier series for non-periodic signals in order to produce the required equation. So, as the period in here, as we treat it tending towards infinity, a number of other limit evaluations happen as a result. So as a result, when we apply all these limits here to our CK equation, that means as we treat the period in here tending towards infinity, conversely, the frequency here is going to be 1 divided by f, which is equal to t. So that means f here is equal to 1 on t as of such, and if we map it back to omega naught, that means omega naught here being our centralized frequency approaches a really small frequency, which we refer to as delta omega. And that also tends towards 0 as of such, because t tends towards infinity, so conversely the frequency here is going to tend towards 0. K omega naught being our individual sideband frequencies and the centralized frequencies, i.e. our harmonics, will also approach towards a continuous omega here as of such. And doing all these evaluations here, Ck here is now going to become a function here of continuous omega. That means the function here transforms this capital C omega here. And the F naught being our fundamental frequency or centralized frequency now tends towards delta omega here divided by 2 pi. When all these limits are applied to our original CK equation here representing our Fourier series analysis, this equation here evolves this capital C omega here, where we apply all the limits as of such to the original equation. So C omega here is going to be delta omega divided by 2 pi, integrated with respect to t here instead of t naught, of common f of t, exponent of minus j omega naught, no, exponent of minus j omega t with respect to dt. And as we can see here, there's no longer any harmonic designator k in applying all these limits. That means we now have an infinite number of k values or infinite number of harmonics, because k omega naught now becomes a continuous omega. And capital C omega here is basically a continuous variable, because t is now infinite. So therefore, instead of having it integrating with respect to t here, and we know t is infinite, we just substitute the t here being infinity as of such for our analysis. So, in observing what we just now did there, the periodic signal, when we had the original Fourier series CK equation, that produced a discretized spectrum from before. But for a non-periodic signal, when we apply all those limits, we end up with a continuous spectrum because of the limit evaluation. And if we modify the equation a little bit, if we juggle it, normalize, and substitute it, and so forth, that C omega naught equation that we have here can be represented as x omega naught with respect to an integral between positive infinity and negative infinity of x of t being our original continuous time signal, multiplied by e to the minus j omega naught omega t dt. And this equation here is what we refer to as the continuous time Fourier transform of our non-periodic signal x of t. So what we just observed here is that how did we do our limit evaluation on the continuous time Fourier series for a periodic waveform for it to be applied to a non-periodic waveform, and as of such, in doing the limit evaluation, we formulate what we refer to as the continuous time Fourier transform of x of t, where x of t here is a non-periodic signal. Of course, because this is also referred to as the continuous time Fourier transform, there must also exist an inverse Fourier transform, which will allow us to move back from the frequency domain capital X of omega to the continuous time domain x of t as of such. And this equation here gives us the inverse Fourier transform. So, just to quickly comment what we're talking about here, the Fourier transform basically allows you to move from the continuous time domain into the continuous frequency domain, and the inverse Fourier transform does the opposite. It allows you to move from the continuous frequency domain back into the continuous time domain as of such. And the combination of the CTFT and the inverse CTFT is what we refer to as the Fourier transform pair, and the Fourier transform is used strictly for non-periodic signals. It can be used for periodic signals, and we will talk about that in later lectures of such, but it comes like if we're just reapplying the Fourier series equations as of such accordingly when we're doing this. And the standard notation for these equations, if you're actually watching these in the textbook, is actual capital F x of t here, and f to the minus 1 if you're doing the inverse for x of omega as of such. And the Fourier transform itself shares very similar properties to the Laplace transform. There are just like one or two important exceptions that need to be highlighted, but we'll talk about those in a later lecture in particular. Alright, so that brings us to the end of today's lecture. And the important thing to take away from this lecture is basically how did we move from the continuous time Fourier series equation by applying limits to formulate the continuous time Fourier transform as of such. And remember, the continuous time Fourier series that we saw earlier on was used for periodic signals. And applying the limits for it to be used with non-periodic signals, we evolved the continuous time Fourier series equation into the continuous time Fourier transform equation accordingly. So the thing that you need to pay attention to in particular are these 5 particular limits as to how we move from this continuous time CK equation here, representing our continuous time Fourier series, and we apply these limits here for a non-periodic signal to evolve the CK equation here into C omega, which we refer to as the continuous time Fourier transform. Alright, so are there any particular questions regarding the material of this lecture? The sinc function on slide 11. No, the impulse contains all frequencies. So that comes back to when you're doing frequency response analysis of any system. Basically, a simple test that you can do is find the impulse response of a system. And the reason why we refer to using the impulse response of a system is to get the frequency response characteristic of the entire system. So because the frequency characteristics of an impulse means that an impulse contains all frequencies, that means you subject a system on the test using the impulse response to all frequencies to see how does the system respond for every single frequency. And as such, an impulse response gives you the frequency response characteristic of an entire system so you can see, okay, the system operates between 400 megahertz to 488 megahertz, but anything outside of that, there's no response whatsoever. So an impulse has infinite frequencies. Alright, nice. Yeah, the explanation on this slide here is also important as well. So just remember the explanation that I told you guys. You can also, when you're reviewing the videos, you'll get back the explanations because obviously it's recorded. And the shorthand here on the slide here, to give you an indication of how do the equations itself manipulates to form the flattened curve and the compressed curve as such. Any further questions? The zero crossing points here in this plot basically refer to where do each one of these plots here intersect regards to the 0 point here. So the zero crossing points will be at -1 here, -2, and -3 as of such. So basically once when the magnitude here is 0 accordingly. In my explanation, what I'm saying is the spacing between each one of these impulses here will start moving apart, and they also start moving together as of such as well. Alright, doesn't look like we have any more questions at this point in time, so if there are any more questions, feel free to leave them down in the comments below. Or you can directly email me as of such, and I'll respond to you guys accordingly. In Wednesday's lecture, we'll be discussing the topic of sampling, as well as the discrete time Fourier transform. So how do we move from the continuous time Fourier transform, which we observed in today's lecture, and doing a little more approximation and limit evaluation, how do we move from that continuous time Fourier transform into the discretized time Fourier transform, which forms the basis of our analysis for any sort of signal in this course in particular. Because like I said, we're dealing with discrete time signals in particular. Alright, so until Wednesday, take care, be safe, and I will see you guys soon. Later.